Oh, yeah, yeah. Also, thank you very much for coming. What should I start with? Yeah, we'll need this later. In 1903, Frank Kohler, I think you pronounce it right, at an MS meeting, he did the following thing for a whole hour. He wrote 2 to the power 67, and he calculated it, half an hour, subtracted 1, then he wrote a very long number and another number and multiplied them and showed this is the same. So this is one of those Mersenne numbers which turn out to be actually not a prime, right? So I want to do the same thing, just draw something speechless, or it was speech, and he got standing ovation. So I was hoping to do the same thing. I'll draw a circle, this is 0, this is velocity, this is another velocity maybe, and this is by drawing this. I might put this here, here, right there. And I was hoping for standing ovation, but I have to explain what it means. Okay, first. So it will be a Hitchhiker's guide to relativistic composition of velocities. I hope you read it, because I'm ready.
No.
Okay. You have to read.
You have to know something about it.
So I'll start with presentation of 3 groups. I'll start with presentation of 3 groups. So it's like a really connection between geometry and algebra, and maybe a little physics. These 3 groups give a solution to the problem. How do you actually add velocities, relativistic velocities, with the pure geometry? And I think this is like a new, fresh solution. Okay. Some of this you have heard me talking about before, but this gives a punchline actually to what I told you before, right? So we really know. So first thing is geometry. Geometry. Okay, so let's introduce the following concept. Let's start with what's a disk? N-dimensional disk. Well, this is all say vectors or points equal 1. It's reverse writing. Right? All vectors inside the thing. Sphere and 1 is simply the boundary of this. So here has to be less than 1. Let's make it without the boundary. And for the drawing, I'll use just a circle as a special case. Circle 1, okay? So let's introduce reversion. So every point P here, or any point P in the disk, let's introduce an operation which itself is from this sphere to this sphere, a very simple one. Point X will go just, and this is point P, will go just across the point. This is, let's call it P of X, where P is this operation, okay? So P is a point. P with dash is a transformation of the circle into itself, right? And then this, a few obvious things. Like for instance, if you square it, it is just identity, right? Because you go there and back. And what else? In general, this is not the same, right? If you go through P and then through Q, this is not the same as going first through Q and then through P. So this is non-commutable, right? So the reversion, let's see, because we're starting with a disk of dimension 2, let's call it reversion 2, we can do it for any n, would be something that is generated by all such operations where P is in the disk. Okay? So clear? Okay. So this is obviously a group, right? This is a group. And you can study some other, this is not assumed name. There is no name for this, so we call it reversion, but if you find a name, so let me know. Now, some interesting thing you can prove is the following thing. If I have like a butterfly situation, let's say, so this, and point there. So like this, and that. So you're doing, okay, and let's put here like a line, arbitrary line. Pick up those 3 points, say A, B, C, D. So this is a very special point which, through these guys, will go back onto itself, right? So you can prove that once you find if there exists such an X, that, what is it, like first on X you're acting with A, then with B, then in this case actually D, and then back to C. If this is again X, then C, D, V, A is just identical. Means start with any point here, and you go this way, it will end up in the same place. So you can sort of like, in a funny way, rotate this butterfly to those 4 points. So this is a polyrism, let's call it a polyrism, and we might actually need it. How do you prove it? So right now we have to use maybe cross ratio formulas or something like this. It might be difficult, but I will in a second show you how to use these. Okay, so that's one group, pure geometry. Okay, second group will be algebraic group. So let me remind something. What is fractional? How is it called? The Moebius group. So start with F being any field, like real numbers, complex numbers, maybe quaternions, or actually we want algebra, right? We want algebra, like division algebra. And we can do the following, we can associate with every matrix the following, and this is the Moebius transformation of our F. Namely, any Z will go to AZ plus B over CZ plus B. It's called fractional linear transformation, or just Moebius transformation. And for short, hide these 3 things, 4 numbers here, Z. This is defined through this way, right? It's like a short notation for the thing. And this is like a matrix M. Both Z and also the numbers A, B, C, D are from whatever you choose here, for your calculations. The thing is that you can very easily show that M and, okay, so if you take 2 such matrices and add from Z through our way, it is the same thing as the regular multiplication of matrix acting on Z, right? So it's like one standard simple thing to check, and everybody should check it once in his or her life. This is really true, right? So this is the famous Moebius group. What else I want you to tell about this? Okay. Now let's look whether, the interesting thing is that we can represent these reversions through such transformations. And here is like maybe like a proposition. One would be this, that if you pick up, so let's pick up our F to be complex numbers, which means we have like a complex plane, right? Argand's plane. And let me redraw it here. Here's our point P, and we want to represent the reversion through this point P. Well, it turns out that this P can be represented by, so these guys are complex numbers of the unit length, right? Any P could be represented by matrix 1, here is P, here is P bar, minus. Okay? So this means that any point Z here, okay, this any point Z will go to some Z prime, namely Z goes to Z prime as 1, okay, 1 minus P bar minus 1, acting on Z exactly this way. Now how do you prove it? Very, very simple. First you have to show that such transformation will preserve the length, equal 1. If you plug in Z from outside, it will go somewhere else, right? But it will be preserved the length. And what else do you have to show? That your P and Z and its inverse are collinear, right? So it's pretty simple to check. But anyway, so we have a representation of this group of reversion, in a sense, okay? And now here, this is the group, right? So reversion 2, this is a group, and this is like a symbol to denote that this is acting on the circle S1. So it's like a one notation. This group acts on this circle. It has a subgroup, say with 0, acting on S1. This is a subgroup of reversions of where the number of those reversions is even, right? Because you have an even number of reversions, you keep it when you multiply, like 2 or 3 or 5, right? One interesting reversion would be something like this. So this is our complex numbers. This is 1, I. You're going first through 0 and then through p. So this is 0, 0. This is z and this is z prime. So what matrix would represent it? Well, first you go through 1, 1, and here a minus 1, 0, 0, right? This is the matrix going through 0. You just plug in p equal 0, right? 1 minus 1. And then through your p, so I can here with 1 minus 1 minus p, p bar. Well, this will be just 1, 1, p, and p bar. Easy to remember. So going through 0 and then through another point is always that sort of a matrix. If you have like many such reversions, you're going through some many, like a knot through between the points, then you just multiply such matrices. Now, if you want to prove, for instance, this theorem here, well, you just take 4 such matrices and multiply them and show them they end up with identity. So that would be the way to prove it. Okay? Now, it would be interesting to see what are, so the group here, we have a group of, if you take those matrices of 1 minus p, p bar minus 1, okay? Like this. Well, they will generate a group. And it would be interesting to know what is this group. It will be a group of matrices. It is smaller than the Moebius group because of the special character. And so I'll be making on the allusion, because I know we have audience, of different areas of mathematics. So I won't explain it here, but this is a special unitary group with the signature 1 and 1 minus 1, and it will be easy to check, okay? With the actually S means special, determinant for 1, actually not true, plus or minus 1. But the group generated by matrices of 1, p, p bar, and 1, these are the even number of reversions, will be a subgroup of this, right? The even subgroup of this. And this would be really SU11. But if you don't know what it means, don't worry about this, okay? But anyway, so we have a group of reversions. It turns out there was an isomorphism with a group of those matrices. So we're done with geometry and algebra, and now let's jump to physics. And here I'm a little scared, because I will try to put only essential points, okay? All right, so physics. I could erase this, right? You don't like it anymore. So in physics, in relativistic physics, there's a problem with conceptualizing things like even velocity, right? And let me remind you one thing. If you have like a platform or a train, let's say this is a train, going with velocity a with respect to the ground, and then here you have another little thing moving. I typically draw James Bond running with velocity v. And here outside of this is sitting and watching this guy. Typically Newton, he had pretty nice hair, but it was really Galileo. So Galileo would say, what's velocity of James Bond? This some kind of composition is simply a plus b, right? And since relativity theory was born, we know this is not true. So let me draw here Einstein has different hair. This is Einstein looking at the same guy, and it was not really Einstein again, but actually Poincaré who first discovered it. A plus b is a plus b over 1 plus a times b, where a and b are between 1 and minus 1, because velocity cannot be greater than velocity of light, and for simplicity, you assume that velocity of light is 1, right? So, in special units. So that's what it is. So this is actually, this addition is a group, so between 1 and 1 and this funny addition is to see that it actually is associative. It's a group of additional velocities. It was introduced by Poincaré in 1904, so not so long after Collet shot this stuff. Very close to Carbondale in St. Louis. And so this is actually not Einstein but Poincaré. But this is one-dimensional case. This is already a little confusing. How can you imagine it, right? Well, if you know the secrets of basic mathematics, this is like tangent formula, right? Except this is not tangent, but hyperbolic tangent, because that's what you have to study. To study relativity is theory of hyperbolic geometry, right? But anyway, I found a way to really imagine it a few years ago, so I'll show you how you can add it purely geometrically. So this is 0, this is 1, you cannot go beyond these things. You want to add A plus B. So this is this is physics. Now mathematics go outside. Draw a circle around, it's a mathematical circle, not in reality. And here's perpendicular guy. And go like this. Go from the top through one of them, doesn't matter which one. From the bottom through the other guy. Connect it, and here it is. This is A plus B. How you can prove it? You can do it just with analytic geometry, like high school method. Get the line, find the point of intersection, and so on. Or you can use this representation and multiply a few matrices, right? Will be another way. And there's another way with using projective geometry. But anyway, that's how you add it. You can even add tachyons. Tachyons are particles which go velocity greater than light. You can move one of these points outside and do the same construction. Should I do it? No, maybe. Adding tachyon. So here is 0, here is, say, velocity A, and tachyon is outside. So you're going this way, here is going this way, and then you connect these guys, right? So look, you have to now extend it here. So look, this is the funny thing, physicists know. Tachyon, if such a thing even exists, right? It's a purely theoretical thing. If you add this energy, it actually slows down. You can see it on this diagram. But it's purely a pedagogical little thing. But I thought then, okay, can you extend it beyond one-dimensional case? In physics, the addition formula for velocities, which are not linear anymore, is really messy. And yesterday, I looked through some basic books, in theoretical physics about relativity theory. Very often it's even omitted, because it looks so unpleasant. So I thought that maybe let's attack this problem and find a method to do it purely geometrically. And here is the solution. Okay. So let me take this away. All right. So I don't know how much you have to know. Well, you know space. This is space-time, right? So this is like x, y, z maybe coordinates, and this is time t. Okay. In space-time, there is a very special structure. Namely, if you want to measure how far this point is from 0, or what is the norm of this vector squared, you have to do like Euclid would do 3,000 years ago, or 2,000, sorry. Squared only, right? Minus instead of plus the square. This minus is the whole secret of relativity theory. Relativity theory is about this funny signature of the norm. And many people say, no, this is about Lorentz group and so on. It's big like. It is really pure geometry. Lorentz group is just symmetry resulting from this, okay? And what is important that if you have time and space, these are depending on the observer, on the particular person. What is important, they are orthogonal, but they are orthogonal in that sense. Because this gives you an inner product to the polarization formula, right? Which is like 1, 1, 1, and for time minus 1. By the way, this is 3, but it could be any dimension, of course, space, and 1 time, right? So, like, for instance, this guy is orthogonal to this. This is why we call this time and this is space. But that's your choice of coordinate system, because maybe this is your life. This is you're sitting in one place and blah, 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 right? But somebody is going this direction. Well, the perpendicular vector will be like this. So this is another split of space-time. And that's what is the relativistic about the thing, and so on and so on. There's a very special set of vectors, these guys, here norm of this is 0. So this is how the line goes, right? Don't look at this, x squared minus t squared, right? X plus t times x minus t equals 0, so this and this. So all possible motions can be within this and so on and so on. Maybe that's enough, okay? Because I cannot just, explain the whole semester thing of relativity theory. Let me show you, if you know, how we deal with this addition of velocities. So I thought about the following thing. For two velocities, what you need is just two-dimensional space to understand it, right? So imagine that you have two-dimensional space, and this is, you build a little planetoid, okay, planetoid of this shape. And you're sitting here in the Buddha position, considering the meaningless of life or something like this, and then suppose you're getting a boost, as you're getting a certain velocity here, right, over there, right, the train. It starts to go. How would you recognize it? So one of the obvious things would be, not to make it too obvious, is look at the stars. The stars will change their position. And that's how you know that now we are in motion with respect to you were just before, yesterday. You've seen maybe some, Star Trek movies or something like this. Did you notice when the spaceship just accelerates in a certain direction on the screen, what happens to the stars? Intuitively, they should go like away, right? But they're actually getting concentrated. And you can actually calculate how they're getting together. So let me redraw it from like Berg's point of view, right? From above. Here you're sitting there. Before this happens, this is what you do. You build a cromlech. Cromlech is, I brought only one, sorry. It's a bunch of stones you put in the field. They have to be much, much bigger than this. On the horizon, you're making, you have Ireland, for instance, in England, right? It is called cromlech. Like Stonehenge is an example of a cromlech. So build something like this, and let me raise this. So if you see here like some star, which is infinitely far away, and you see here, you see from this direction, make it like unit, whatever is your unit, and put a stone here and mark it. This is this particular polar star or something. Here is another star, this one, and this one, and this one. So all these points on this circle are really rays towards stars. On this picture, maybe you can ask me later, what does it mean in the space-time picture? But anyway, so these are the null vectors in the space-time, right? Because they are rays of the light coming to you. All right. Now, once you start to move, positions of the stars will change. And that's why you can detect, okay, now I'm in a motion with respect to what I was. And I simply, let me take this away. So I just calculated what it would be, and the trick was this. Okay, once again, let's put here the motion in this direction. So let's see with velocity v. Okay, we start to go with velocity v. I just look what happens to particular star, any star, okay? How far this goes. So you can look what happens to its x. If you know the position of x, y would be, x squared plus y squared is 1. So you know what is y. So you need only know what happens to x, right? So the new position of the star would be, is it still a circle? It will be something here. So this x prime, okay? Now if you calculate it using this geometry, this is what you get. The new position would be old position plus exactly the velocity over, I think, 1 plus x times v. Kind of like similar, but different meanings, right? Okay, so that's kind of a proposition, and of course I won't be proving it here, but you can always ask me how you do it in just 3 lines. Now, notice one thing now. Okay, what's happening? What's happening to this star? I mean, star is over there, but to the position of this star. So 0, right? 0 will go to a new position, which is exactly plugging 0, right? V. Going to V. What's happening to this star which you see in front? 1. If plugging x equal 1, so 1 plus v is going still to 1. Right? What about this star behind you? -1. So plug in x equal -1. -1 goes to -1. So these two stars stay, right? And the one to the left and to the right, they move to the new position, and it will be exactly whatever is the new velocity you're getting in. So if you're in galactic scout or something like this, on this planetoid, where is it? Oh, here, you're on the planetoid, and your body is made a prank, and they, at night when you're sleeping, they put the thing in motion in some direction. You can easily, guess what happened. Just look for the two stars which did not change their position. Okay, that's the direction. And then look at the one which was exactly on the left side. How much did it move? That's your velocity. Okay. All right. So the next step would be, we don't need to prove it. So the next thing is this. Maybe some vocabulary. So as I told you, this is called promenade, right? Promenade is this stones representing it. Now let's put a man here, just a simple stone somewhere. Look, if you start to move this direction, you could put here a stone which will represent this particular velocity, right? It's like our point. But instead of this, we'll do something else. Okay? So once again, suppose this is your velocity. We represent this velocity by a diminished velocity, let's say. A stone which will be sitting inside, and that's how we construct it geometrically. Put here vertical to your velocity, and here combine this, but similar to this guy. This is a different point, right? Put your stone there. And like single stones standing in British Islands are called Keystone or menhir. They call it also menhir. Well, it's Celtic languages, right? Menhir? Menhir. Let us be God to understand what I'm saying. So I'm after two. Okay. So put a menhir, and this is like representation of your velocity. So every velocity, let's call it, mu, will become mu of v, sometimes simple n, menhir of this velocity. We represent this velocity. Why do I want to introduce this? Because of this, what you can now show, that the motion of the stars here, this is star S, and this is position S prime, right? So they move. The motion S prime will be simply take your S, kick it through 0, and then through your menhir representing velocity. Let me put that. Okay? So this means, if you want to know what happens to this star, you're going through 0 and there. Well, this we knew. It will go to the velocity. But what about this star? What happens to this star? Well, you go through 0 and then through your menhir. This is S prime. What about this star? It's going through 0 and then through menhir. That doesn't change. What about this star? Going through menhir, through 0 and then through menhir. What about this guy? Through 0 and then through menhir. This star will go there, and so on and so on. So we're getting a very simple representation of what's happening if you see on the stars, how the stars, right? What velocity it corresponds to, and vice versa. If you're given velocity, build a menhir, and menhir tells you exactly what each star actually did on the thing. So you have a deformation, deformorphism of the sphere, right? So, how would you prove it? First, we have to know if this is, so this is maybe proposition 2, very simple one. Namely, this corresponds to this, how they are related to each other, okay? So you can calculate easily that velocity and menhir are like this. If menhir is on the real axis, that's what it is. Velocity is slightly longer, okay? And how do you prove it? This thing is becoming very interesting. So let's go back to this, right? You have this construction. This is velocity, and this is the point you have to calculate. So what do? You just consider this triangle and this triangle to be similar. You're getting a few ratios, and this is like a very simple homework. This is what you'll get eventually, okay? And then if you want to see how this, I think velocity maybe, velocity and Menke, how they are related, if you want to graph this relation. Well, if Menke is here, velocity is here, so 0 goes to 0, right? And easy to see that 1 goes to 1. So Menke is always closer to something like this. Okay? So every velocity, and it's written by Menke, is a little closer to the center. You might also calculate like at what moment they differ like at most. Well, you calculate the difference, take the derivative, and surprisingly, this velocity, which is the most distant, that Menke will be most distant from actual velocity, and this is the Menke corresponding to this, is exactly golden ratio. I leave it to you to discover it. So it is phi in the sky, not phi in the sky. And okay, so that's how you prove this. How do you prove this? Same thing. Let's draw. So suppose here is maybe here is your man here, okay? And here is maybe. Okay, I don't want to even go maybe here. Here's your arbitrary star. You're going through this, right? And then through man here. So notice that your star has particular x, and the length of this is your y, and of course x squared plus y squared is 1. And so notice that this is also, the length of this is y, okay? And so this triangle is similar to this triangle, okay? And this is after the motion of the star. This is s prime. This is x prime. This is what your original x. So notice that y prime to this means x prime minus men here, position of the men here, is the same as y to this, right? So as y to, and this is men here, simply. Okay? So now use this formula that represents y prime, just square both sides, right? Square both sides, so you're getting that y prime squared will be 1 minus x prime squared. If you square this, or just square it. Square it, solve it for x, right? So I'm skipping this, and just in a few lines you should get something like this. You can reorganize it until you get this. 1 plus n squared, and here 1 plus x times 2n plus 1n squared. So just solving this will give you this. But this is exactly what we want. Remember with our proposition number 1. 1 plus v. Okay, so the position of the man here has to be chosen this way for the geometry to work. So we're getting exactly the motion of the star. So we sort of proved this proposition that yes, this double, kick through the 0 and the point gives you exactly how the stars move on the sky. Okay, so anything is maybe unclear. Okay, so now let's go to this addition formula. Maybe let's do some experiments first. So what if your bodies played twice the Frank overnight? Means they first accelerated in one direction and then in another direction. That would be like adding two velocities, right? So we have now a geometric way to do it. Suppose first this is the man here corresponding to the to accelerating the thing in the velocity v. So this is not velocity. This is man here 1. Velocity is a little farther, right? Remember the formula of the thing. So this is man. So first you push the thing to move with certain velocity in this direction. And then maybe with certain velocity m2, right? So you're getting up at the morning and you're looking for the two stars which didn't change, and this will be the velocity, the corresponding sum of the two velocities, right? That's what you think. But look what happens. Take any star. So we're going through 0, and then through n, and then through 0, and then through n. You know what? It doesn't tell you anything. I want to show you first one thing else, okay? Let's go back to this butterfly theorem I did at the very beginning. So, to go with any star through 0, and then there, okay? So, through 0, and then through point as in meant here, is the same thing as first going through minus n and then through 0, because of this theorem at the very beginning I mentioned. So you can always replace the order of this, change the order of this, but you have to replace n by minus n. So point minus n, right? Okay, so instead of through the origin and n, it's the same thing as going through minus n and then to 0. And this is actually very symmetric, not in my drawing, but it's like so symmetric that this is like obvious visually. But you can prove it directly from this butterfly theorem I started with, okay? Well, what does it give you? It gives you maybe a simpler way to deal with adding two velocities. So suppose, once again, this is 0. This is Menhier number 1, and this is Menhier number 2, okay? So the addition of the two velocities will be something like this. You're going through first O and N1, and then through O and then N2. So N star goes through O and 1, through O and then 2, right? Looks kind of confusing, but you can change the order, I think best of the second one, right? O, and then just O, and minus N1, like this, right? Just change the order. But what is O with O? Going there and back. So it's identical. So this is just N2 composed with minus N1. Okay, so this means that if they indeed play the prime with two velocities, then, so this is 0, this is N1, and this is, say, N2. So we can simply do what happens to this particular star. It will go through negative N1 and then through N2. So through this to this, right? Any other star through this and then through this. Okay? Can we replace it by a single Menhier? Well, not anymore, because notice, like, okay, what if I combine this line? What happens to this star? Through this, let me write it here. Through M1, minus M1, and M2. Doesn't change the position. What about this star? Through this and back. So if you're getting up next morning, you see that these two opposite stars, which shouldn't change, are not aligned with the center, but they are off. So this is not anymore a single boost. And that's the whole problem which Einstein didn't understand, actually. So composition of two velocities is not a new velocity. It's a velocity plus 7 rotation of the whole thing. Okay, that's why. Which, if you know group theory, is kind of obvious, because if you compose two hyperbolic rotations, now it will be a new mix, right? We'll have this component, hyperbolic component, and just oriented. It's like obvious. But Einstein thought that no, there is a simple formula for adding velocities, and it is even associative, which was one of his big mistakes. So people published many papers later, this is not associative. But here it is obvious, right? So composition of the two things is something more complicated. It's just single Menhier. You can find here a single Menhier, but it has to be mentally composed with rotation. Okay? And everything becomes here kind of like maybe messy. Okay? But if you forget about this the rotational component, you want to know what is this new Menhier, Well, that's the thing I started the whole talk with, okay? And so that's the maybe ultimate answer to the question, how do you add velocities? Okay, maybe like a diagram. So you have two velocities, v1 and v2, and you want to have this thing, right? What is the final addition for those velocities? This is what you do. Go and represent them by men here, m1 and m2, two men here. Okay, so this is our map mu. Okay, so you bring those men together. Now here you add these men here in a certain way, which I didn't say now earlier, m1 and m2, to the new men here. Okay, and this is the same thing corresponding to velocity v1, v2. Do everything with men here. And here, this is argument, okay? And why this is working this way? Okay. So look, this is what you do with the velocity 1. So you put here, var, var. Remember, this is the algebraic representation of this double thing, through 0 and through n, right? So that's it. This is number 1. Or should I call it A and B simply? But they are men here. A, okay? Men here. A, men here, number 1. And then you multiply by men here, number 2. And that will be composition of two velocities in any direction. There are two complex numbers. By the way, you can redo it with quaternions, but you have to be very careful because of the non-commutativity, right? But so let's multiply these two matrices. Okay, 1 times 1 plus, okay, 1 plus b a bar. And again, with quaternions, you have to remember which direction. What about here? A plus b. And here is b bar plus a bar. And then here will be a b bar plus 1. 1 plus a b bar. Let me put here a this complex numbers. So these slightly different, okay? Now remember, these matrices are up to a number because look, if you have ax plus b, this is just pure algebraic thing, right? If you have something like this, if you multiply both the top and the bottom by the same number, the result will be the same, right? But if you multiply outside by some alpha, this is the same thing as alpha a and alpha b. Here x plus, and then here cx plus b, right? This is obvious. So this means that you have alpha times matrix A, B, C, D, understood as a Moebius transformation. It would be alpha A and alpha B, C, D, right? If this is from outside. If you make it like 1 over alpha, this will be the same thing as multiplying by alpha at the bottom. If you want this thing to still mean the same thing. So look what we can do here. From the top, let's kick out this 1 plus a bar b, okay? And therefore, this becomes simply 1. This will become a plus b over 1 plus a bar b, okay? Now, from the bottom, actually we can take this out. But here we go as a denominator would be like 1 plus a b bar. And here we have 1, but here we have a plus b over 1 plus a bar b, big bar over the whole thing. Okay, so if you compose two velocities, two boosts, right? You accelerate this direction, accelerate this direction. This is the same thing as, this is class from the previous civilization. You're getting again a new boost. This is the new velocity. This is the new velocity. But then you have to multiply by a number, by a complex number. This complex number is unit, because notice that this is just conjugation of this, right? So this is like e to it. This is the rotational part. So with this, we're getting, okay, two boosts give you a boost by another direction, right? But then you have to remember to rotate it a little. And same thing with quaternions. It's a famous relation with quaternions we show up here. Okay, so this is our next maybe like a proposition. From this, we're getting the composition of, here. This is our, so we define this the following ways. n1 plus n2 divided by 1 plus n1 bar n2. And everything became very simple. Now notice here is still visible maybe a little. Poincaré formula. Poincaré formula for vectors was of the very similar form and very simple. For nonlinear vectors, this is something some people are ashamed to put in physics books, so some complaints. But if you reduce velocities to those menhirs, suddenly this thing becomes very simple, and you can deal with matrices. Okay. Now the last thing would be, I have like huge commuting diagrams of all those groups, but I will maybe not do it. I'll just maybe explain this one picture of how do you add right velocity. So maybe. Okay. So this is the last theorem. Let's say geometric construction of this. Okay, which really is the same as just one man here and another man here. Our addition, right? Because it doesn't matter. It's just reduced version of velocity. So that's what you do. Really, from the picture, I already remember I go through this and through this, through those two velocities, this minus m and so on. You have to subtract the rotational part, and it is really difficult. So I made a huge diagram one night. Like by 7 a.m., I knew it. I saw it. The next day, I looked at this. I couldn't recall so many steps of simplification. So I tried to look at my solution at least. And I managed to simplify the solution, and I don't know how to get there, but I know how to prove it at least. So it looks like from nowhere, okay, but it is really something like this. So because I'm in a hurry, so I better make sure I don't make any mistakes. So here is A, okay. So this is 0, right? This is maybe A, the boost number 1, but this is men here, not velocity, but just men here, corresponding to this. And let's say this is B. So this is how you construct this new velocity, which you still have to compose later with velocity, with the rotation. Namely, go with it doesn't have to be a real number, really, right? Just two numbers. Draw this line here, add the endpoints, and make a perfect circle through 1, 2, 3 points. Okay? That's your circle number 1. Then do the following thing. Take this B and take it on the other side. Okay. Now, take these guys, connect with one line. So these are not opposite points anymore. And go this time through 0. These points will intersect, and this is exactly A plus B. Okay? Now, how would you prove it? I have like a few minutes. So maybe that you not prove, but how will you prove it? Right? What do you think? You know, it's a cross ratio in geometry. Cross ratio is one of the maybe let me introduce cross ratio. What do you think? Quickly. So if you have 4 points, complex or real numbers on the line A, B, C, D, cross ratio is a certain invariant with respect to Moebius transformations or just pretty much this is it, right? Moebius transformations and anything else? Yeah, just Moebius transformations. You can calculate this way. Draw such a thing like a meander. Okay? And every time you go from this to this, just subtract any direction, say from this to this. If you look at the top, A minus B, and C goes to D, C minus D. And here you're going through D to A, so D minus A. And then here you're going from D to C underneath, so B minus C. I copy it because this is not known. So this is the simplest way to find this invariant, which is called cross ratio, A, B, C, D. Okay? This is something which is preserved through Moebius transformations. For instance, they could be complex numbers. Okay, so that's what we have to use. There is a theorem that for 4 points in a convex plane. If this cross ratio of those 4 points is a real number, then they are definitely cocyclic. So that's what you do here. Just take this point, this point, this point, and this point, and show they are cocyclic. Just plug in. You know what is this? -1 plus 1. You can always make this real, right? The 1 plus -1, d you know, and this one, use this formula, and just calculate this one. and you get there. So this is done. Now this one is tough, because you can show that this and this and this and this are cocyclic, but these numbers are really tough to calculate, like across this. You don't want to do it, right? So then I thought about something else. Make an inversion of this line through, of this line. Make inversion through this circle. And as you remember, if you make inversion of a circle, it will be another circle. This guy at 0 goes to infinity, so the image of this circle will be this line. This stays, this goes here, and this goes somewhere there. Now, what is important only is to check whether this point and minus b are collinear. And that's very simple. As complex numbers, the difference divided by difference has to be a real number. And this is only this. And you get it. So that's how you prove it. So I have a proof that this is the right point, but how I got there, there was, you transform your brain sometimes overnight when you're writing a program into something completely else, which does thinking for you, and you never will understand this, your alter ego, right? So yeah, okay, so that's the geometric way to add velocities. So I guess that's the idea.
Okay. Thank you. Are there any questions?
Yeah.
Right.
And always remember to have it with you. If you have a question why, ask people who are laughing.
Or you will explain this at the coffee.
At the coffee, yes.
So
Coffee with me.
Okay, let's thank you.